All right, so this is our electron diffraction setup here. What we have here are two things. The first one is the high voltage power supply. It can go up to 5,000 volts. And the next thing is the electron diffraction tube. So this is a vacuum tube where basically we have some tungsten filament somewhere inside. And the tungsten filament generates electrons through thermionic emission, right, Doug?
Yes, sir.
It's called thermionic emission or thermal excitation of electrons through some tungsten. And these electrons are accelerated through some acceleration plates between the cathode and the anode, and then they gain the accelerating voltage which is generated by this high voltage power supply. And then as you see here, I'm going to have a close-up of inside. You see there are different things in there. Most of those things are for focusing purposes. So you want to be able to focus the electron beam so that the electron beam is basically nice and thin, nice and sharp. And at the end, let me see if you can see it. There is a, you see there is a little hole with something in the hole. I think you can see it. What that thing is, it's a nickel mesh, and on the nickel mesh, there is some graphite powder deposited on the nickel mesh. So the electrons are going to go through the graphite powder, and then when they go through the graphite powder, they are going to get diffracted. So basically, the electron diffraction is going to go through, it's going to happen through the electrons going through this amorphous graphite powder. It's amorphous, it's not in crystalline form. Amorphous means the crystals in the graphite are oriented in random direction, so that they will basically go through some randomly oriented graphite lattice. Again, if you can look there, you can see the nickel mesh, and of course you're not going to be able to see the graphite deposits on it, but that's what it is. So that's our target. So this is our target, what you are looking at. And then on the front of the tube, there's a fluorescent screen. So you cannot see the electrons by naked eye, obviously. Electrons are invisible. But when the electrons hit the fluorescent screen, they are going to generate a dot or a circle of diffraction pattern. So the reason why you'll see those dots and circular patterns is because of fluorescent screen. And again, inside there is vacuum. If you didn't have vacuum, then the electrons would be absorbed and you wouldn't be able to see anything. Once again, this is a close-up of the electron tube. Let's go over the connections here quickly. So we have like 4 wires. The green wires are for the filament. As Professor Berg is pointing out, it's 6.3 volt AC. And the red wire is for the positive high voltage. It's nice and insulated, as you see. It's an insulated connector so that you don't get an electric shock. And the black wire is for negative connection. These wires go on the back of the tube, so if you could gently raise it. So the green wires are connected to the filament terminals. The black wire is connected to the cathode. And finally, the red one is connected to a terminal called G7, I believe. Somewhere there. Let me see, where is that picture? I think there's a picture in the back or on front maybe. Yeah, so if you could get a shot of that. So these are connections right here, you can see it. All right, sure.
So it's important to keep in mind that you'll see this when you look at your lab manual write-up, but these wires are going to go into the filament, and the filament gets hot through I²R heating.
Like a light bulb, right?
Like a light bulb, yeah. Mm-hmm. And that causes, temperature is mechanical vibration. Mm-hmm. And when the mechanical vibration, which are also quantized vibrations called phonons in a solid, when the energy of those phonons is on the order, gets to be statistically averaged around the work function of that filament, it'll pop electrons out, and then they're popped out of the filament, and they're sitting there, and they get sucked through the accelerating voltage. This phosphorescent coating here is the positive terminal, and they come from the negative bias toward the positive terminal, and they go through accelerating voltage, picking up their speed.
Right.
Yeah.
Yeah. As Professor Burke said, basically, when you heat the filament, the electrons overcome the work function of the filament. If you remember from the last experiment where we were doing photoelectric effect,
Yes.
we were looking at the work function, right?
Exactly.
So it's the same thing here. The electrons, they need to overcome the work function through thermal excitation.
Right. Now, I have to correct one thing. When the electrons are thermally emitted out of the filament, they then get accelerated through a constant voltage, which will adjust here on this knob.
Right.
Okay. Then they continue on to this this phosphorescent screen. Now they're going to go there. They've already picked up all their speed in here. What I said earlier was, it could be interpreted that they're being accelerated from here to there. They're being accelerated from here to here, and then they have their speed, which is well defined, which is their momentum, right? MV. And then after that, they continue on to the phosphorescent screen and make their mark. And you'll see these circular patterns on here. Now, as you said in the introductory lecture, if you had two principal maximum as dots, and then the orientation planes of the graphite is random, it'll give you every possible orientation here, which traces out your circle. So, anyway, just a slight correction there. I don't want them to misinterpret what I said. Yeah.
Yeah, right. So, and then they will see at least two circles corresponding to different lattice spacing on the graphite.
Okay.
So graphite is two-dimensional lattice, stacked two-dimensional lattice.
And what's wonderful is we have a knob here, and that knob will change the momentum of the electrons, and the diameter of the circular pattern on here is a measurement of their wavelength.
Right.
So it gives us the de Broglie relation, which is really what we're after.
Right. So that's right. Exactly.
And what we'll do is, as we adjust the voltage here, the diameter of these circles will change, and I'll come in here and put the measure. I'll measure the diameters with this
right
caliper.
So you need to be able to read it both on the core scale and the vernier scale. Make sure when you take the measurement.
So we'll take a measurement like this, and then I'll place it down here, and the camera will come up to this point.
And then you look at the vernier scale.
Yeah, you want this is each tick down here is a millimeter, and then you get fractions of a millimeter by using this instrument as you've been instructed.
Right here is a vernier scale, and then you need to teach yourself how to use the vernier scale if you forgot. Okay. But there is a vernier scale here.
Well,
so
they've learned that in earlier physics courses.
They probably don't remember, but
well, they can review it.
Why we do a light bulb here? Yeah, here. That's good. So we have our overhead lights.
Yeah, so we'll have the lights out, and you'll be able to record the voltage here, and then the diameter of the rings here.
One thing about the thermo-ionic emission. So you can ask yourself, how is the temperature related to the work function? So basically, if you remember from Physics 151, the energy is given by temperature in kelvins multiplied by the Boltzmann constant, right? It's kT. Right. The energy is K, which is the Boltzmann's constant, multiplied by T in kelvins, in absolute temperature. So kT gives the work function. So if the temperature of the filament is 1000 Kelvin, or let's say 1500 Kelvin, it's probably around 1000 Kelvin, right? So that's what I would guess. And 1000 Kelvin times the Boltzmann constant, how much it is, it's probably around several thousand, several electrons. Maybe about an electron volt, Doug? Something like that.
Yeah.
So they need to, I mean, you can look it up. So you can calculate how much kT is in terms of electron volts. So all you need to do, look up the Boltzmann constant, multiply by the temperature, which is probably around 1000 Kelvin, and then you divide it by the charge of the electron, which is 1.6 times 10 to minus 19 coulombs, and that gives you the electron volts in terms of electron volts. So it's going to be probably around 1 electron volt. So this is our work function. But anyway, so that's just some side note, just in case you are curious how the temperature is related.
Well, they can verify those numbers very quickly because they know Boltzmann's constant, and they can, in fact, determine the. They can take let's say they take a good calculation is to take a metal like gold and look up the work function, and then find out how hot it has to be.
Right.
For the
or you could
for KT to be on the order
look it up for tungsten, right?
For tungsten, yeah, which is what the filament.
Yeah, and then when you do that, remember to convert it into electron volts. So you divide it by 1.6 times 10 to minus 19 to convert to convert from joules to electron volts, because normally KT is going to give you joules, and then when you divide it by the electron charge, then you get it in terms of electron volts. Okay.
Okay.
And this is just going to be basically on the order of a volt.
Right. So again, your data is going to be the accelerating voltage, which is going to give you the speed of the electron with a correction factor in your lab manual.
All right. So
and then the diameter of these rings.
So now, before we turn this on, make sure that the high voltage is off. That's crucial. Okay. Make sure that the high voltage is like all the way down, turned down to 0.
Counterclockwise, yeah.
Yeah, counterclockwise. Once you make sure that, then you turn it on. As you see now, my voltage right now is showing 0.00 kilovolts. By the way, what you are seeing here is in kilovolts, so it's 1000 volts, okay? So if you see 1 here, it means 1000 volts, not 1 volt. Okay, now we are going to wait for 1 minute. The reason why we wait for 1 minute is
the filament's got to get hot.
Yeah, the filament needs to get hot, and if we don't wait before the filament gets hot, then what happens is that we might damage the filament. Thank you.
Yes.
So to protect the filament, we wanna wait for a.
Now, also, when we see 2 rings here, the broader ring is going to be the smaller gap, and the tighter. The smaller ring will be the wider gap. Those 2 numbers that are given in your lab manual for the two diffraction, like the grid spacing. Right.
All right. Can we turn off the lights now?
Yes, sir.
Thank you. Are we ready to do? By the way, before we turn on the high voltage. Okay, you guys now can see how the filament is glowing in there, so I'm trying to focus. Okay, I think I focused.
Would you like a spotlight in there? Or?
No.
Okay,
I'm just showing them the filament, because if you turn on the lights, they won't be able to see it.
Right, okay, right. They see the glowing. That's the tungsten glowing.
Yeah, so it's basically just a tungsten wire, just like a light bulb. As you see, if you remember from the previous experiment, blackbody radiation, the first experiment, the color of this filament is related to temperature. Right now, the color is kind of like orange. What does that mean? If you remember from the first experiment, blackbody radiation, we did not really show them actually the picture of the filament there when we did it.
Right, because you couldn't see it too well. We had one angle.
Yeah, but as you know, the color becomes like more yellowish when you increase the temperature or the voltage, and eventually becomes almost white. So right now it's almost like between red and orange. So that means the temperature is probably around 1000 volts. 1000 Kelvin.
Well, they could take the wavelength of orange light.
Yeah.
and you know they know the first.
Yeah,
of
I mean,
Newton's
of course,
laws,
it's
and
not,
they
it's
can
not, it's
determine
not,
the
it's,
temperature.
that's not going to be very accurate if you do it that way. So you would have to do like a black body spectrum to get the temperature, right? Just like we did in the first
Right,
experiment.
or they could use that the
But,
wavelength is equal to constant over the temperature.
But
from
you
each
know,
wall.
the color is not like white, which means the temperature is more like 1,000 degrees rather than 2,000 or 3,000 degrees.
Kelvin, exactly.
In Kelvin.
Yeah.
All right. So now,
Now, are
I'm
you going to be able to see my calipers here?
Well, before we, I mean, this is the second part of the experiment. We are
Right, we'll
not there
take the
yet.
data, yeah.
But we are going to do the electron microscopy first before we do that, right?
Right. Let's just show them that it
So
works.
first,
yeah.
I'm gonna let me bring this a little bit closer.
Point this toward you.
No, I
that
got
better?
it.
Okay.
Yeah, I got it.
Okay.
So maybe let's focus there. So now you can see the voltage and the fluorescent screen at the same time. So I'm increasing the voltage now. So now we have only 170 volts. You don't see anything. So right now we are not seeing anything on the screen. So maybe you can actually even turn off that light over there.
Can't see anything because the
So maybe that's too dark now.
we'll have to take this data with the
Okay.
lights on because
Yeah. Let's turn on. It's gonna be. Oh no. Doug. If you can
This
just.
guy?
Yeah, that's enough. That's more than enough.
Is that enough?
Yeah, that's more than enough. But we'll see if they can read the caliper with. So right now I'm about 1,000 volts.
Really good signal.
Okay,
There we go.
now you see. Now you see the electron, central electron dot there. Let me focus in there. It's appearing a little bit larger on the video than
Now the wavelength
actual.
is too big now, so as you turn up the voltage and or speed of the electron, you'll
Yeah.
focus. You'll see it come into focus. You'll start to see rings that are
Yeah, I think-
small enough to be on the screen.
I think you can barely see the rings now. Some of them. But let's keep going. Maybe now you can turn off that light so
Yes,
that.
yes.
Okay. So I think that's better maybe.
I can
So-
see the rings. Can you see them in the camera?
Trying to focus. I think they can. Oops. Yeah. So right now I'm 1700 volts. Yeah.
So where did you want to take your first data point at? 2,500 volts?
Doug, we are not there yet.
Right.
We are going to do the electron microscopy first.
Okay.
And then once we do that, then we are going to take data.
Okay.
I think you guys can see it. They can see it in the video too, right? The circles here.
Yeah, I can see it in the video.
So these are our diffraction pattern. So right now we are at 2.5K. It's actually more than 2 circles, but when we do the experiment, we are gonna do the 2 main circles, but it's more than 2. What you are seeing there, you are seeing multiple circles corresponding to different spacing on the lattice. So there's obviously more than 1 spacing on the lattice. But the 2 of them are like the main circles. So these are like the ones that we will be doing.
Coming up to 2,900 volts there, yeah. You see them getting tighter slowly.
Trying to get a good focus there. I'm going to sub at 4,000 volts. Okay. So this is just about 4,000. The knob setting, okay, so that's 4,000. So let me see if I can get a little bit better focus there. It's kind of overexposing a little bit, so it's a little bit hard for them to see the circles. I wish I was using my Pro Video mode so I could change
You
the.
want to turn the
Yeah,
light
give it a
off
try.
a
So
little bit.
maybe we'll see better.
Can give you a little bit of light. Does that help you? With my naked eye, I
okay,
can see
so yeah, they are gonna have a.
there you go, right there. See the dark circle now? There you go. There you go.
So maybe when I hold it closer.
Yeah, with a little bit more light on it. Yeah, now they can see the different rings more clearly.
Okay, so now this was our introduction for the data taking. So now I'm gonna stop the video for a second, and I will also try to adjust exposure in the next video so you can see the pattern better, okay? So this concludes our introduction. So now we are gonna take data in the next video.